All right, hello again. Just following up from this. We did figure out the phi factors. The basic idea on the phi factor here is that for the base metal shear strength anyway, we were having the phi factors for the base metal. I have some better equation numbers on here. This here, the base metal shear strength, this is coming from, effectively, these are from equations J4-3 and J4-4. And if you notice on the 50th edition of the AISC manual, that is going to be on page 16.1-137, and that does illustrate that for shear yielding in the element, we're going to use a phi, for the base metal anyway, we're going to use a phi equal to 1.0, and for shear rupture, we're going to use a phi equal to 0.75. So I couldn't recall where that came from exactly, but we did, I had it in my notes, but I had to double check that. Okay, so let's continue on, and I might work through a brief example here. So, let's see here. Now, let's work through this example. And make sure we're recording. Yep. And let's work through this example. Given. Well, let's say an MC 10 by 22 C 10 by 22 A992 steel, steel member is welded to a 3-inch thick, or sorry, a 3/8 inch thick, inch thick, a 3/8 inch A36 gusset plate, using 3/16 inch fillet welds. Uh, 3/16 inch fillet welds. With E70 connections, or with E70 electrodes. So basically we have this. Oh, that doesn't look good. So you have an MC 10 by 22, MC 10 by 22, and connected to this is some sort of fillet plate, or sorry, some sort of gusset plate. It's connected to a fillet plate. That makes sense. This is going to be connected to a gusset plate. And the thickness on this is going to be 3/8 inch, a 3/8 inch plate. And this is MC 10 by 22, and the point load is going to be, or the tension is going to be pulling this way, P, here. And I have a weld along here, all the way along, and I'll give you the dimensions of this. And I'll give us the dimensions of this. Well, the dimension this direction should be no surprise. This is 10 inches for the MC 10 by 22. This is 10 inches, but then this had to be designed, and this is 16 inches. And I want to find, let's say find The max service load that can be applied if the live to dead load ratio is 2.5. To dead load ratio is 2.5. If the live to dead load ratio is 2.5. And then investigate all limit states. Investigate all limit states. So we want to look at all the different ways this member can fail and all the different ways the welds can fail, the base metal, all this kind of thing. Okay, so let's work through this. First, solution. This is an MC 10 by 22, and I do need some basic properties. So from the table I can find the gross area, AG, is equal to 6.45 inches squared. X bar is equal to 0.900 or 0.990 inches. Then TW is equal to 0.290 inches. 0.290 inches, and the D, the depth, is equal to 10.0 inches. Then for the A36, in terms of material properties, A36, here, Fy, the yield strength, is going to be equal to 36 KSI, and an ultimate load Fu equal to 58 KSI. So that's for my A36, and then for A992, which the C10 by 22 is made of, the yield strength is going to be 50 KSI, 50 KSI, and the ultimate strength is 65 KSI. Okay, so let's go down and look at all of the different ways this thing can fail. So we're going to actually have to go back and we are going to have to go back and borrow some things from our earlier unit, our first unit on tension member capacity, because this is a tension member. So the first limit state I'm going to investigate is GSY, gross section yielding. Gross section yielding. And phi T, that would be a phi for tension times Pn. In this case, it's going to be 0.9 times Fy area gross, Ag. So that'll be 0.9 times 50 KSI times the gross cross-sectional area of 6.45 inches squared. And this then comes to 290.3 kips. So we have our first limit state here. Then I want to look at net section fracture. So net section fracture. And here, phi T, Pn, would be equal to 0.75 times Fu area effective, AE. And area effective is just going to be equal to U times area times the gross area, because there are no holes here. So this should be a review from our tension member design earlier in the semester. U is going to be equal to 1 minus x bar over L, which is equal to 1 minus 0.990 divided by 16, which is equal to 0.938. 0.938, which then means that area effective equals, if you multiply 0.938, so it's going to be 0.938 times the gross area of 6.45, and the effective area then is going to be 6.051 inches squared. 6.051 inches squared, and I know I'm gonna move through this fairly quickly, but I do have a lot of ground to cover. So phi T Pn is going to be equal to 0.75. I'm gonna move quickly, especially through the tension member part. times 65 KSI, 0.75 times 65 KSI times the effective area of 6.051 inches squared, and that comes to an overall capacity of 295.0 kips. So that's another limit state. Next, I want to look at, now, I don't have to worry about block shear rupture on the member because it's, you can only have block shear rupture when you have a block that can actually tear out. There's really no block to tear out except the entire plane of the member. So, but block shear rupture can be a factor for our gusset plate here. So block shear rupture, I'm going to look at the gusset plate here. Here, gusset plate. Block shear rupture on the gusset plate. So, phi Rn is equal to 0.75 times 0.6 Fu ANV, the net shear area, ANV plus, let's say that is going to be equal to UBS, U block shear times Fu ANT, and that's less than or equal to 0.75 times 0.6 times Fy AGV plus UBS Fu ANT. Okay, and this should all be fairly familiar. ANV, the net shear area, is equal to just the gross area because there are no holes. Again, because there are no holes. And ANV is equal to A, so there's that. And let me actually calculate that. It's going to be 2, because we have 2 shear planes, 2 times 16 inches, the length of it, times 3/8 inch, the width, the thickness of the gusset plate. 3/8 inch, and that is 12.0 inches squared. And then area net tension equals 10 inches times 3/8 inches, 10 inches times 3/8 inches, and this will equal then 3.75 inches squared. So therefore, once calculating all this, putting this all together, phi Rn is equal to 0.75 times 0.6 times 58 times 12 plus basically, here. Basically, I'm going to calculate both sides of this equation, here and here, and the phi is already baked into this. So this is 0.75 times 0.6 times 58 times 12 plus 1.0 times 58 times 3.75. And this is then less than or equal to 0.75 times 0.6 times 36 times 12 plus 1.0 times 58 times 3.75. And then if you collapse this, we get that phi Rn is equal to 476.3, which must be less than or equal to 357.5. The smaller controls, and for the state of block shear rupture on the gusset plate, we get that phi Rn is equal to 357.5 kips. So we have one limit state there. Okay. Now, one question we might look at is, why am I not I'm not going to calculate net section fracture or yielding on the gusset plate. Now, we don't usually calculate yielding on gusset plates because they're simply not large enough for yielding to be a factor. But what about, why am I not calculating net section fracture on this thing? Any idea? I'm not calculating net section fraction on this because I don't actually know the width of the plate at any given point. I don't know the height of the gusset plate at any given point. Basically, on this, we're going to assume, for this particular problem, we're assuming that the gusset plate is very wide, and so it won't fail in net section fracture. Okay. So up to now, everything here has just been standard tension member design, like the kind of thing you've seen previously. Next, what I want to do is calculate the actual capacity of the connection, and that is going to be the weld strength. So let's now move on to the weld capacity. Let me save this first, in case this thing decides to crash again. Okay, moving on. And I want to calculate the weld shear strength, so let's look at the connection capacity. And to do this, again, with the connection capacity, I'm going to, connection capacity. And to calculate this, I'm going to look at both the weld shear strength and the base metal shear strength. So here, let's consider this. Now I want to get the strength. Now I do want to get the strength per inch. So calculate the weld and base metal shear capacity per inch. And so for the weld, well, VRN is going to equal 0.75 times 0.707 times 0.707 times W times 0.6 FEXX, the yield strength of the electrode, or the strength of the electrode. And so this is then 0.75 times 0.707. We have a width of 3/16 of an inch, 3/16 of an inch times 0.6 times 70 KSI. And this comes then, VRN for the weld is equal to 4.176 kips per inch. 4.176 kips per inch. Now we'll then need to use this to calculate. Our capacity. So VRN then for the weld. So we have our weld. Again, I'm doing this as a strength per inch kind of thing, and then the base metal. VRN is equal to the minimum of 1.0 times 0.6 Fy times T, the yield strength times the thickness of the plate, semicolon, 0.75 times 0.6 ultimate strength, Fu times T. So if you calculate this, or if we put in values, VRN is equal to the minimum of 1.0 times 0.6 times the yield strength of the plate of 36 KSI, 36 KSI times 3/8 inch, and then the minimum of this term and 0.75 times 0.75 times 0.6 times Fu times that would be 58 KSI times the thickness, which is 3/8 inch. And this comes to then, if you plug and chug on that, the minimum of 8.1, 9.788. 9.788 here. 9.788. All right, moving along. Okay, Now, I do want to give one note on this. Notice I'm calculating the strength of the base metal for what element? Am I calculating the strength of the base metal for the gusset plate or for the MC shape? Good. I'm doing it for the gusset plate. Now, if you're just doing two plates, often what you're going to have to do is you're going to have to compare the. You might have to look at both of the elements. Now, for this particular one, the gusset plate is going to be 3/8 inch shear. Well, basically, if we look at this, if I consider this, how can I explain this? The gusset plate is going to be made of material that is much weaker than the MC shape here. So it's going to control in this particular case, but if we wanted to be right and proper, we could actually calculate the capacity for both of these. But if I was going to do this really properly and list absolutely everything, I would calculate that as well, but this example is large enough, or long enough. So phi-rn then is going to be equal to we go with the minimum, 8.10 kips per inch. Now, so we have the capacity of the weld and the base metal, both in terms of kips per inch. Well, how we handle this is we go with the minimum. So the smaller controls, therefore, phi-rn is going to be equal to 4.176, or 4.176 basically kips per inch. 4.176 kips per inch. Now, here, since weld shear strength controls here, since the weld shear strength controls rather than the base metal, we apply the equations we saw previously. We apply, just like we saw previously. Oh, let's see, get our equation numbers here. That was 2-6. Yeah, we're going to apply 2-6A and 2-6B. Apply J2-6A and 2-6B. And so J2-6A, if I work through this, phi-rn is equal to phi RWL plus phi RWT. And we already have the we already have basically the strength of each of these in terms of length, or in terms of length, capacity per length. So we just need to multiply by the lengths here. So this is 4.176 kips per inch times 16 inches plus 16 inches. This is the length of the longitudinal weld, length. And plus 10 inches. 10 inches, this is the transverse weld length.
16 times 16 or what?
Plus 16. 16 plus 16. This is the transverse weld length. So we have these two things. And if you multiply these, or if you add that up and multiply together, you'll get that phi-rn is equal to 175.4 kips for equation J, for the case of J2-6A. Next, I want to look at J2-6B. J2-6B. And here, phi-rn is equal to 0.85 times phi RWL plus 1.5 phi RWT. So here we don't just add them up, we add some multipliers. And this is equal to 0.85 times 4.176 4.176 times the overall longitudinal length, which is 16 plus 16, plus 1.5 times 4.176 times the transverse length, which is 10. And we get that a FERN is equal to 176.2 kips. FERN equals 176.2 kips. Okay. And this one will control for the connection. It's the minimum value.
Could you go back one slide real quick, because I didn't get the final FERN, 175.
Yeah, the final FERN here was 175.4, and the final here,
What's that?
let me double check something here. 176.2. Yes, actually, that is kind of interesting. In this particular case, notice it actually says on the language there that we do choose the larger. That is the one case that one of the few cases you'll see in the manual where the larger actually controls. The larger actually controls. And so let's do a summary. Let's look at a summary here. Actually, maybe I'll do this on the next slide. Summary. Gross section yielding, GSY, is going to be phi PT is equal to 290.3 kips. Net section fracture, phi PT is equal to 295.0 kips. BSR, block shear rupture, phi PT, or FERN in this case, is equal to 357.5 kips, and the connection, FERN is equal to 175 or 176.2 kips. And this one will control. So now that we just need to apply the relationship previously. So notice we said previously we had that ratio between dead load and live load, where we said live load was equal to 2.5 times the dead load. So I can just apply this now. So again, this one is our overall design capacity. But then I want to go and calculate the service load. And so calculate service load. And I can say that P ultimate is less than or equal to FERN. And here, but we already have that. PRN is going to be that 176.2. So, but P ultimate here is going to be equal to 1.2 times P dead plus 1.6 P live. And so then this is going to be, but 1.2 P dead, and then I also know, but remember I was told that the P live is 2.5 times the dead load. 1.6 times 2.5 P dead. So this comes to 5.2 PD. And so 5.2 PD is equal to 176.2, so therefore PD is equal to 33.9 kips. And P live then equals 2.5 times that, times 33.9, which comes to 84.7 kips. So that means the overall service load with this load ratio the overall service load, P service, will be simply 33.9 plus 84.7, and this will be 118.6 kips. And so this slide here is just an application of the definition of service loads, load ratios, etc., etc. All right, so any questions on this? Again, I really like this example because it goes through sort of the chain approach, where we look at all the different elements, all the different types of failures that can occur in a connection, and it also brings it back to the types of tension member design we saw earlier in the semester. So, and it does illustrate how to calculate the connections, how to calculate the capacity of welds, and all of those things, and I do like how it brings everything together. All right, that'll do it for this portion of the lecture. Thank you for watching, and as always, thank you.